All right. Hello, Sarah. It is Mike. This is a video right for you. And I am just going to close a couple things here and then let's get into this. So, welcome to solutions video number 1, functions. You thought that other shit was hard. Welcome to grade 12 functions. I've been giving you some easier stuff. I also sent you an email so you can check that out. That's kind of the style of problems. It'll be a little bit easier, right? That stuff's probably, let's say, an 8 out of 10 challenge. I'm probably going to give you a 6 out of 10, but you'll have to know the concepts. So 10 question quiz every day is going to help sort of guide your learning in that as you're working through functions, and especially through con and the other hard skills. So I am going to start with one thing at a time. So first off, you've been doing these already with con, and you're making good progress. F of x equals 3x plus 8x. Here's what this looks like, right? First of all, your algebra skills still work. So if you see 3x plus 8x, you instantly know that's 11x. But what is this f of x thing? Essentially in math, as you get farther along, a function is a thing that you do to a variable. The function takes this input and spits out an output. It's kind of like x values go into the box, and then out of the f box, and then out comes some new value that you've normally known as y. But y is now being called f of x. It's kind of like saying I f'd the x here. So I took the box and I did the f to the x. Other than that being kind of awkward to say and maybe offensive, then that's kind of what you're doing. So whenever you see f of x, it's easiest for you to just replace it with y. Okay, so y equals 11x. But in the question, I gave f of 3. So while you can think about this side like y, we've basically been told x, this value is replaced with all the x's. So what do we do? Well, anywhere there's an x, so if I have y equals 11 times by 3, then I got 33 here. So 3 times 11 is 33, y equals 33, or I can also say that f of 3 in this case is 33. So things to take note, again, f of x is just y, but when you're given a value, you got to plug it in to all of the x's. This will get a lot more complicated. The other questions that you're working on also have g of x, and that equals some stuff. So obviously you can have these intersect with each other, but whatever you end up calculating, you just replace it back into the function itself whenever you need. So in this case, the x was 3, you put it in for the x, and you get f of 3 equals 33. So I hope that is helpful for the first one. The second question, we want to simplify. So what the heck does simplify means? It means make it, reduce it to its simplest form. So if I have 8x squared y, and it's over top of 2xy, there's a couple things you should see here. First off, you should see that because this is this, divide this, you can actually factor these down. So you can say this is 4 because you divide by the 2. You can say that you get rid of this x, and you get rid of the x squared, which is just x times x, so you get rid of one of those x's, so you're left with x. You get rid of y because you've got a y on the bottom. So when you simplify this, it turns into 4x over nothing, or over 1, which is just 4x. So this simplifies to this. You're going to see a lot of different kinds of problems where you get to cancel things out and like rearrange and draw things out and cancel them. So I just want to start you thinking about this really important algebraic tool, which is simplifying things. So simplifying in this situation, that's 4x. Hope that is straightforward there. Question 3. Question 3. You are going to factor. Well, factoring is basically simplifying, except it's breaking it into parts that are easy to understand. We do this, so factor is like break into parts. So factoring, you might have 6 and you break it into 2 and 3. So 2 times 3 is 6, but if we factored 6, we'd break it into, this is called prime factoring, into its parts. For the question that we have, we are looking at this thing, 2x to the third plus 4x squared plus, that should read 2x. And I'm sorry that it doesn't. So that should be 2x there. So we want to factor this. So we're looking to remove or break things down into its parts. You should do a lot of practices of these. I will be giving you these every day because these should come completely naturally. First thing that you should see in all of these terms, there is what's called a common factor. A common factor. Now the common factor is the thing that you can take out of each of these. And I'll give you a hint, it's 2x. So when you pull 2x out of each of these, you're left with 2x times all this stuff. But in that first one, the 2 is pulled out. This turns into an x squared. Now I've got plus, because I've still got this term, so I pull out the 2, so I've got 2 left. And then I pull it on x, so I've got x. And then on that last one, I pulled out a 2x, and I'm just left with 1. So I'm done, right? Wrong. There's still more factoring you can do. You should remember to last year where, and you're going to have to warm up for this again, this actually further breaks down. You've got 2x times two different things. I've got x plus 1 and x plus 1. How did Mike do that? Okay. So x times x is x squared. X times 1 is 1x. 1 times x is 1x. So I've got that other 1x and this 1x that gets me 2x. And 1 times 1 is 1. This is a quadratic. I factored it into its two factors. Yeah, this is a perfect square. That's what that's called because these two things are the same. Do you need to know that? No. But this is the full factoring of this full line. I pulled something out of those terms, and then I got down to this. So first things first, pull out common factors. Second thing, you have to recognize for grade 12 math, when you have a quadratic, that it should be able to factor to this. Sometimes it can't. For our purposes, I am only going to give you ones that can, or I'm going to make reference to it. So that you should get comfortable with going between these things. So that is breaking it apart into factoring, and that is question 3. Question 4. Question 4. The question that I gave you is about radians. So just to take a break before we start, radians are measured in terms of pi. Wild, right? What the heck is a radian? It is an angle. You know how in distance we have like feet or we have like meters? So those are the same, but you can convert, right? So it's like 3.35 feet goes into 1 meter. You can convert between those in distance. These are annoying. Sometimes you measure someone in like 6.5. Sometimes you measure like how many meters away something is. Same thing with angles. There are 2 different ways to measure angles. This is a really big deal. One of them is degrees. You're used to 90 degrees, right? That is a right angle. The other way to do it is to say in radians, it's pi over 2. 90 degrees is the same thing as pi over 2. Literally the exact same thing, like no difference. Why do you need to know this? You actually just need to know it. It's for trig. This is much easier for trig, working in radians in the kinds of questions that we're going to work in this year with you. So you need to know these. So we're going to go through lots of examples. I'm going to give you lots of time to figure this out. But the major translation that you should always remember is pi radians equals 180 degrees. So no matter what I do, if I go pi over 10, well, that means this divided by 10, and 180 divided by 10 is just 18 degrees. So pi over 10 is the same thing as writing 18 degrees. So you should see that kind of translate through. So this particular question was pi over 2. So pi over 2 is literally just take pi and divide it by 2 to get me 90 degrees. All I'm going to ask you to do is translate. I want you to just almost without hesitation be able to tell me what pi over 4 is, pi over 6, pi over 8, you will probably not have to know. But there's going to be a bunch of these, and just translate them through. So that is the translation of radians, which is a little complicated. But that's question 4. Question 5. Question 5. We're starting to get into some trig here. Now, remember, the sine of 30 degrees, not 30%, 30 degrees, is 1/2. So, what the heck is going on there? Well, you can put that into your calculator. You can do whatever you want to this, but that's the answer that it's going to spit out. So remember, you take in your calculator, you hit 30 and you sign it, and then it spits out a number. But what happens if I don't have this number or this angle, but I do have something over here? So how do I do that? Well, I am going to take out my fancy calculator here, which looks nothing like yours, so I'm sorry. And I can't actually do, that's funny. I can't actually do inverse sine on that. So let's see what's going on here. Oh, yeah, there we go. So, I got my other calculator here. And so normally I would just do 30 sine. Nope. I would do it the other way. I would do sine of 30, and it would be 0.5. Okay, cool. But what if I need to go the other way? Well, then I do this thing called second sine. Second sine. And it says a sine. It's the opposite. And if I put 0.5 in there, that gives me 30. What? So second sine of this number gave me the angle. So in this case, we have sine of some angle that we don't know. We're going to call this theta. This is a really popular number. You can call it x, whatever, but you should get used to different variables. Sine of something equals 0.7071. All right, well, how do we do this? We're going to take and go, again, I hit sine, or second sine, so it's a sine. And I'm going to take 0.7071. And that's going to get me 44.999945. What do you think I was trying to write there? Well, clearly the rounding didn't work so well. So theta equals 45 degrees when I really write that down there. So the angle that I'm working with is 45 degrees using that second sine function. So you got to get real familiar with that in trig as well. We're really diving into it now deeper. All right, Sarah, here is question 6. And it's this thing right here. And you're like, Mike, I hate you. And I'm like, yes, I know. And then I'm going to say, I warned you not to take grade 12 calculus or grade 12 functions. And you're going to be like, shut up, Mike. And I'm going to be like, yeah, exactly. So this thing you have to memorize. It is like a requirement of grade 12. It is one of the big units. It's like 20% of what you do. And it's the basis of all trig. Here's what the heck this thing is. You'll notice you're starting to learn radians. This is the radian of this angle. You'll also notice that if I were to draw a straight line out to that point, that angle there is 60 degrees. Also here, this angle would be 90 degrees. Now, you're looking at different sections of the circle, and we can see that everything is positive in this section of the circle. All of these values are positive. But in this section of the circle, we actually have these first values, which are negative. So it goes negative and then positive. Well, what the heck does that mean? Turns out that for the brackets, the first value is, I don't want to tell you the wrong thing, so I'm just going to look it up super quick here, because it's been a while.
How can we tell whether the cosine or sine of an angle is positive?
All right, so cos is positive here and here, so it starts with cos x. I should have remembered that. And then sine x is next. What the heck are you talking about, Mike? You will see in a moment. Here, both are positive. Here, both are negative. Here, cos is positive and sine is negative. I'm going to give you this sheet to work with. Basically, this gives you all the trigonometric ratios for any value in the unit circle that you would need. This is called the unit circle. That's 180. That is also 0. What are these numbers? When you take cos of 60 degrees, cos of 60 degrees is 1/2. Sine of 60 degrees is √3/2. That is like truth. You can do it on your calculator and you're going to end up getting √3/2. The way in which we're doing this is based on the two common triangles. One of them is a 45-degree angle triangle on both sides, and this is 90. And the other one has a longer side and a shorter side, and this is 30 degrees, this is 60 degrees, and this is 90 degrees. In these two triangles, these are the side lengths of things. 1, 1, and √2. How did I do that? Well, I could do a squared plus b squared equals c squared. That's how I could solve that. Or you can just memorize it. So, in this case, this is 1, 2, and √3. So, the longest side is the hypotenuse, that's 2. √3 is this side closest to the 30 degrees, and closest to the 60 is 1. These are truths. These are just triangles. These are base root triangles for 30, 60, and 45 degrees. Now you'll notice from the good old days when you had cos is adjacent over hypotenuse, you'll see that cos of 45 is going to be adjacent 1 over √2. But hold on, let's go back up to this circle. Cos of 45 is 1 over √2. Turns out that is equivalent. Turns out √2 over 2 is the same thing as 1 over √2. This is just a fancier way of writing it in math. Let's do another one here as an example. How about cos of 60? Well, you should remember it's adjacent 1 over hypotenuse to 1/2. Cos of 60 should be 1/2, and boom, it is. When you get really good at this and you memorize this, Sarah, I can tell you, I can give you, hey, Sarah, what's cos of 2 pi over 3? And you're like, well, I know that's right here. I know cos is the first one. It's -1/2. And drop your pen and be like, whatever, Mike, I got this. This isn't as overwhelming as I thought it was going to be. This is all the information that you need to do cos and sine of any of these radians in here. And so I hope this is helpful, and I hope this makes sense. And if it doesn't, we're going to chat lots about it, but I'm going to ask you to watch this video like 100 times. So I hope that works. Thanks very much, Sarah. All right, so question 7, we're talking about log. Log is an exponential thing that helps us measure how fast things go. It's all about things that are like increasing at extremely fast rates. So first thing that you need to know about log is that there is a phantom number here. It's 10. We call that the base. Log to base 10 of 1. Now when I do this in my calculator, I get 0. That's kind of like a truism. And I will prove to you in a moment why that's the case. So first of all, let me kind of show this on the calculator. So I hit log on my calculator, Now, I don't have to write the base because that's implied whenever I don't see it. So log of 1 equals 0. So that is true in the calculator sense. How the heck did I get that? Well, it turns out if I want to convert this into exponential form, and I'm going to basically be asking you to convert these into exponential form like all the time, just so you get really familiar with it. The base is like the big number. And then this 1 is like the number on the other side. But this 0 is like the exponent. Well, it's not like, it is. So why do we have different ways to write exponents? So 10 to the 0 is 1. Well, I could also do that, right? I can pick up my calculator, and there's this button called XY there, and I can say 10 XY, that's to the 0, equals 1. Okay, well that's true in my calculator. This is just a truth. And so 10 to the 0 equals 1 is a truth. So keep in mind that this base is like the big number. This 1 is like the answer. And the log of 1, this side is the exponent. So it's almost like log allows us to search for or calculate the exponent, which is super important. So this translation, don't forget, on this side for log is the exponent down here. And so we're solving for the exponent that we don't know. This is how logs work. This is how they're translated. And then for the question that I said was, what was log of 1? Well, that's actually log to base 10 of 1, because 10 is like the phantom number that's always there, equals 0, because this is a truism. Any number to the 0 is just 1. So I hope that is helpful for question 7 there. Question 8. Question 8. In any graph, the number of different directions that it goes gives us the degree. So if it goes like this, this is degree 2. If it's just a line, so if it's like this, that is degree 1. If the graph goes like this, then this is degree 3. Well, how did I do that? So I basically said it goes up, then down, then up. And so if you count those, it goes up, down, up. That's 1, 2, 3. It's that many degrees. So sometimes these can look quite different. They can have really like tight changes of direction. So it can look like this. That is still a degree 3 because it went down for a little bit and then it went back up. So you count it, it's going up, then down, then up. You can also, and we'll talk about this a little bit more, but you can also have it go up and then go perfectly flat and then up. And that flatness actually does count as a change of direction. So this would be, so it would go up and then there's a change. And so given the way that I've written it, so it would be like down and then up again. So this would also be a degree 3. So as long as there's like changes, so it's up, then it's like neutral, then it's up, or like completely horizontal, that's still 3 degrees. That's still a degree 3 function. The questions that I'm going to ask in question 8 have all to do with how many degrees. So we can look ahead to more challenging questions, and I would do something like this. So it goes up, down, up, down, up, and that's going to be a degree of 5. So you're able to solve the degree by how many times it changes. You'll also notice that if something ends and finishes on the same direction, that's an even number degree. So this would be up, down, which is degree 4 there. So that is an even number because it ends facing the same direction. Now, next up is the the positive or negative leading coefficient. So the leading coefficient. Essentially, exponents make things happen much faster than anywhere else. So in this function, we said it's an x to the 5, which means that if we write it out, we got y equals something, we don't know, x to the 5. Now, we don't really care what the number is here, but we care if it's plus or minus. Now, Sarah, the big question here is when you have a negative times a negative, you get a positive. Now, what happens if you times it by another negative? Well, you get back to a negative. And what happens if you times it by another negative? Well, you get to a positive. What happens when you get to another negative? Well, it becomes negative. So, if x was really negative, was down here, so x is a negative number, x to the 5th is going to be a negative times a negative times a negative times a negative times a negative. So the way I always like to simplify these is I like cancel them out. So that becomes a positive, that becomes a positive, that's a negative. So this is overall negative, which means y is going to be negative. So if this leading coefficient is also a negative, it's going to cancel that out, and then y would have to be positive. We're dealing with a lot of negatives here and positives, but essentially, when you do this logic on this x, in this case, the leading coefficient must be positive because a negative times a negative times a negative times a negative times a negative is a negative number. It's down here on the graph. So this is right. This goes off and keeps getting more negative. And that biggest one is going to force it to be more and more and more negative. If this is a positive, that is true. But if this is a negative, this number out front, if this is like negative 7, x to the 5th, then the whole thing would be flipped. And this would actually end, and the tail would end up. So in this case, because the tail ends down, I'm showing you the math here, that you can say that the leading coefficient is positive for this because this turns out to be negative. Let's do this one. So you should be able to use the same kind of logic. So if x was negative, well, we know it's 4 of them, right? X to the 4th, because it's 1, 2, 3, 4 changes of direction. So we're trying to figure out what the sign is of the number in front of the x to the 4th. Now, if x is really negative, we've got a negative times a negative times a negative times a negative. But, so if you cancel those out, you get a positive. If you cancel those out, you get a positive. A positive times a positive. So, Sarah, as x gets more negative, in this case, it should actually get bigger. It should be more and more positive above the x-axis. But it's not. So how did we turn these positives into a negative? Well, we put a negative number out front, which then flipped the entire thing, which meant that this number that should have been really positive is now really negative here. So in this graph, I can tell you the leading coefficient is a negative value. In this graph, I can tell you that the leading coefficient is a positive value. I've given some complex examples here. We're going to work through these a little bit more, but you should be able to say, okay, it's a degree 4. Should this be positive? And yes, it should. Or is it pointing negative? Is it pointing down? In which case, this leading coefficient must be a negative. So things to think about there and continue to practice and work through. So in the problem specifically that we were given something like this, well, that's a degree 3. And is the leading coefficient, is that positive or negative? Well, a negative times a negative times a negative. Well, that's a positive times a negative. So overall, as we go into the negative space, this should be negative, which is true. That's what I'm seeing. It's going down. So that means the leading coefficient must also be positive, because the positive times the negative keeps it a negative. So the leading coefficient is positive, and that's the right answer there. So I hope that helps give you an understanding. And question 9. Question 9. We want to graph. And we are going to graph y equals x squared plus 2x plus 1. Now, Sarah, grade 12 math is where you really start to see these things without, with knowing all the different kinds of math that you know, with knowing the factors and things like this. So for example, if I'm able to factor this into x plus 1 times x plus 1, you might remember from last year that this is actually, these are the zeros, meaning that when I graph this, and so it's the same 0, so when I graph this, when x equals negative 1, this points up. And so this is basically my graph. Now, if I wanted to be even more specific, I know that this is the point 0, 1. How did I know that? Well, when x equals 0, that goes away, and this is left just plus 1. So I know this is the point negative 1, 0, and I know this is the point 0, 1. I got 2 points on my graph. I know it's a parabola because it's x squared. Boom. So I just did a few different things there to triangulate. So that's where your brain should start going. You have multiple skills, multiple knowledges, and reads of this thing, but the good old conventional way is always the T-chart. So Sarah, even if you can't get to a place where you're seeing this in your head, at least the T-chart will be able to help out. So first off, let's pick values of 0, 1, and 2. Now, because you're in grade 12 math, you also have to pick values of negative 1 and negative 2. There's weird stuff happening in the negatives, and you've got to be able to pick that out. In grade like 9, 10, 11, you could get away with this. You need to add the negatives here. So if we plug 0 in, that becomes 0, that becomes 0, this becomes 1. If I put a 1 in there, 1 squared is 1, plus 2 times 1 so that's 1 plus 2 is 3, plus 1 is 4. 2 squared is 4, plus 2 times 2 is also 4, so 4, 8, plus 1 is 9. Now negative 1 squared. Negative 1 squared is just 1, plus 2 times negative 1, so that becomes negative 2. This is 1, and this is 1. 1 minus 2 plus 1 equals 0. Okay. And then negative 2, so if we plug negative 2 in there, well, that becomes 4 plus, it's actually minus 4 plus 1. 4 minus 4 plus 1 is 1. So Sarah, you should see a little bit of a pattern here, but if we actually plot out those points, remember x is the left, right? So we got 0 and 1. Remember that from the other graph, so we seem to be doing well if we're checking. X is 1, y is 4. Okay, that seems to be right. If x is 2, y is 9. That's cool. Now, if x is negative 1, y equals 0. Okay, that seems familiar from what we had. And if x equals negative 2, then y equals 1. And that looks a heck of a lot like the other graph that we had. Remember, it's a quadratic. Remember that it opens up because there's a plus or minus value here. You can do the same thing with the degree and leading coefficient that we did before. So hopefully that is helpful there, Sarah, for graphing quadratics. You're going to get one of these every week. These need to be fluid and just bang on. Starting to think about, okay, what is this x-intercept? What's this y-intercept? How did I figure out anything else in this graph? So, and then question 10. Question 10 is also graphing. Now, you can get some help with these, but again, you can always use your, you can use the internet and Wolfram Alpha, but you can also just use a t-chart. Don't forget that this also looks like 10 to the y equals x. You remember that from translating logs into quadratics? So this is the same thing as writing this, but we're going to write it in this log form because it's easier to manage. You don't know the math to be able to work that other piece. So create a t-chart, x and y's. We might need a little bit of help with this. 0, 1, 2, minus 1, minus 2. So let's actually take some different numbers here. And so I'm going to backtrack that. I'm going to take log of 0 first. Log of 0. Oh yeah. So log of 0 isn't getting me anything, so we're gonna write like a little like question mark there. So then log of, let's try 1. So log of 1 is 0. Now let's erase that and let's try log of 2. We're going to get 0.301. All right. Well, let's try log of negative 1. So log of 1, or of negative 1, is also not really giving us a result. And let's try log of negative 2. So it seems like we can't do like log of these negative numbers. So Sarah, you might see this and you might be like, what the heck is going on? So if that's the case, trust your instincts and also trust the math. So it seems like log doesn't like these negative numbers, and it also doesn't like this 0. So clearly there's something going on there. So why don't we switch to a positive number? And let's say if x is 3. So if we do log of 3, well, that equals 0.477. 0.477. All right. Well, maybe we need to pick something a lot bigger. So let's try x is 10. So we pull that back. We say log of 10 equals 1. Oh, right. Okay. Oh, yeah, that makes sense. So now I'm remembering that when I take log of larger numbers, like when I take log of 100, I get 2. So log of 100, well, that equals 2. So when x equals 1,000, then y equals 3. Because log of 1,000 equals 3. All right, so I should be able to use all this info to graph something that looks like log of x equals y. So let's give this a shot. So I've got a graph. This 0 doesn't make sense. This like negative, when x is on this side, it doesn't make sense. But let's say when x equaled 1, y equaled 0. So here, it seems like that's a point on the graph. X is 1, y is 0. Now if x is 2, it equals like something that's like super close to 0. And we said x equals 3, it also equals super close to 0. And when x equals 10, then y equals 1. Okay, so it seems like this thing like gets real right real fast. Now something weird is happening in here, and this is where as you figure out these functions, you're gonna have to figure out like, okay, well this is 1 and this is 0 and didn't like 0. I gotta figure out what's going on in this space. So let me try here log of 0.5. So if I did log of 0.5, oh well, okay, cool. I got, 0.5 gets me negative like 0.3. Okay, what if I do something even smaller, like 0.1? Oh man, 0.1 gave me negative 1. Okay, so could this be doing something where like if I do 0.1, yeah, 0.01 gets me negative 2. So if I graph these, 0.5 is like here, negative 0.3 in the y. Then 0.1, which is just on this side, equals 1. 0.01 equals 2. Oh man, okay, so we got a graph now. Then this gets really close, but never touches that line. And you just graphed using a t-chart y equals log of x. So I hope that is helpful and you're not too overwhelmed.